Thank you everybody for being here. Today we have Professor Nicholas Pizzo, visiting us from the University of Rhode Island. His talk is Upper Ocean Currents. Brief introduction. Professor Nicholas Pizzo is an assistant professor at the University of Rhode Island and is in better understanding the physics of polar atmosphere and of the ocean, he uses theoretical, numerical, and laboratory approaches to better understand these processes. So, over to you.
Thank you. It's wonderful to be here. So today I'm going to talk about upper ocean currents. To orient us, this is a photograph taken 100 miles west of San Diego, California, showing where the air and sea meet. So I want to explain to you why I care about upper ocean currents. We're then going to talk about the submesoscale ocean dynamics experiment. This was a big NASA campaign a few years ago. Before getting into what I'm calling GOFLOW, it's some work I have in press right now. If there's time at the end, I'll talk about some other stuff we're doing at the Surf Lab. Please feel free to ask questions. This feels like kind of an interactive audience. If anything's confusing, let's stop and discuss. Okay, so let's start with the thought experiment here. This is 2017 as part of the ONR-sponsored Langmuir Cell DRI. This is the research platform FLIP. Has anybody ever seen this? It's essentially a cylinder that's 350 feet long, fills with water, and just the last 75 feet stick out. So you get towed out to sea on this thing. The moment of inertia is really small. You're always in the trough when you're getting towed out. And then it takes about 20 minutes as you start filling with water for you to go about 20 degrees. And then in about a minute, you go the remaining 70 degrees. This is Laurent Greer here. He's an air-sea scientist. And you can see there's a lot of kind of incident waves here. This platform is extremely stable. It's been used for a number of very well-known air-sea interaction studies. And this is a great moment as you're flipping upright. But something that wasn't obvious to me, and you can see the excitement here, something that totally wasn't obvious to me the first time I went out, is that essentially it's like a floating treehouse. And being on flip is really about being at height, setting up instruments. So here I am on the port boom, setting up a thermistor chain. I put a GoPro on my head. You can see what it's like to walk out on these booms. So this is 2017. For reasons I don't remember, we never set up the guideline here. You can see a series of laser wave gauges here. We set up all these instruments. And the reason we're doing this is we're outside of the superstructure of the ship. But at a practical level, when you spend your time for weeks on end kind of setting up instruments here, when we set up some IR imagery, there's all these anemometers. Laurent had a boom with a series of anemometers. If you're a clumsy theorist like me, what you start to think about is, what would happen if I were to slip? You have enough time to start refining your questions there. So then you can ask, well, where would I go? And really what you want to know, you see, this is the chase boat here. So then, you have enough time. You're out there all day. The question you really want to ask is, how am I going to move relative to flip? But we're scientists, so we say, okay, we can formulate this a little bit more sharply. What is the horizontal divergence at the ocean surface? This is really the question we're asking. And when you start thinking about horizontal divergence at the ocean surface, you're really thinking about some mesoscale ocean currents. These are fronts, filaments, and weights which support a lot of the horizontal divergence at sea. Their horizontal length scale is on the order of 100 meters to tens of kilometers. Their vertical scale is on the order of 10 meters to 1 kilometer. And they have a time scale that goes from hours to days. What I'm showing you, I don't know if you can see this very clearly, this is a photograph taken by astronaut oceanographer Paul Scully Power. And this is all marine kind of flotsam that is in these convergence zones, and it traces out these spirals here. This bar is 10 kilometers. So these spirals are all at scale smaller than 10 kilometers. These are those submesoscales that we're talking about. There's a recent review where they talk about why they're important for vertical motion. So if we have the continuity equation and we just do some scaling, the vertical velocity will scale as this aspect ratio h over L times some characteristic velocity scale. So if we have a velocity scale of 10 centimeters per second, you might expect the velocity from the mesoscale somewhere between 1 and 10 meters per day. Whereas from the submesoscale, it's something like 100 meters per day. So this is between 10 and 100 times larger than those mesoscale motions. So this has been capturing everybody's attention in physical oceanography because it's thought that this is important for moving things from that mixed layer to depth. And those things are things like heat or biological or chemically important processes. So people have been very interested in this. This is a false color image off the coast of San Francisco showing chlorophyll A concentration. This bar here again is 100 kilometers. And all of this small scale motion is what we call the submesoscale. We sometimes call this the submesoscale soup. And we think that the ocean, parts of the ocean at least, are completely kind of saturated with this submesoscale soup. Now, something dynamically is very interesting about submesoscale currents as well. So if large scale flow is quasi 2D, it has an inverse cascade. That means that energy that starts in smaller structures will go to larger structures. Here's an example on a sphere, starting with a random distribution of vorticity. And we're solving Navier-Stokes equations on the sphere. And what you're going to see is basically a Bose-Einstein condensate that forms of just all of the energy going into these large vortices. Oops, that went the wrong way. So you start with small scale structure and then you end up with bigger scale structure. The mystery is that dissipation acts on small scales. It acts on these large gradients. How do you dissipate energy that's at these large scales? It's thought that these submesoscale motions are a conduit between that quasi two-dimensional mesoscale motion and fully three-dimensional turbulent dissipative scales. So modelers are very, very interested in getting these submesoscales into their models and resolving them. Now, people have known this for a while. At least the last few decades, people have been talking about this. But the elephant in the room is that these things are really too small for many remote sensing footprints, but they're too large and too fast for shipboard instruments. So this again is flipped. The Sally Ride is in the background. We were chasing some mesoscale features here, but it's very difficult to get full environmental coverage with platforms like this. So the question is, how do we measure some mesoscale currents? So this is the question we asked in the NASA suborbital S-mode campaign. So it's the submesoscale ocean dynamics experiment. And the central question was really a technical one. It's, can we measure submesoscale ocean currents? So we had this combination of instrument packages and payloads on airplanes, so we weren't on satellites, as well as all these in situ assets like a research vessel, Lagrangian floats, there were wave gliders. In our first pilot campaign, there were sail drones, as well as surface drifters. The goal here really was to test this instrument from JPL that was on this aircraft here to see if it was well suited to be on a satellite mission. And we did 3 campaigns. There were at least 50 people involved in this. Maybe some folks in the room were involved in this. The experiments happened off the coast of San Francisco in this polygonal zone here. And you can see all the ship tracks and the tracks from the autonomous vehicles and the uncrewed vehicles. The wave gliders came out of Santa Cruz. And we did a lot of the flights out of NASA Ames. So the third IOP was in April of 23. We're going to talk about that a little bit. And the campaign or the mission wrapped up last year. And just to get a picture of the environmental conditions, this is just SST from Veers with geostrophic product on top. And this is a 10-kilometer bar here. So you're really seeing the large scale structure. There's a lot of mesoscale motion here. We were there mostly in the spring. And again, we're interested in measuring these very small currents that are on the boundaries of these mesoscale eddies and other mesoscale structures. But it's worth taking a step back for a second and remembering what we're doing here. This is a video taken from the research platform Flip a couple days after those beautiful photos were taken. The wind is blowing at about 10 meters per second. The significant wave height is 4 meters high. And we want to take measurements in this region to get some information about currents in the upper ocean. there is a lot going on here. You see swell propagating from the upper left to lower right. There's active braking going on. There's the advection of that foam. You can see waves coming almost in a transverse direction across the swell. And then there's all these bright lights that you can see. Those are these tiny parasitic capillary waves that are forming in these regions of large curvature. So it's worth, again, thinking about where we want to make statements about the currents. I just want to wait for this large breaker to come through because I always enjoy watching this. This one right here, maybe that's the next one. So again, the question is, how does one go about measuring in this area? And we're going to see why historically it's often been ignored. But the thing we want to also keep in mind before we move on is that the vertical velocities from the waves are orders of magnitude larger than the vertical velocities from these submesoscale currents. So it's going to be very, very difficult to directly measure any of these submesoscale currents. And so what we do is perform something that's not really novel. It's what people have been doing for a long time. We're going to use the waves not as noise, as something to just average over. We're going to use this as signal to better learn about what the currents are doing. And the idea is that we have two of these suborbital payloads on airplanes, DOPVIS from Scripps, doppler-based from JPL, and we want to know what's happening right in the upper ocean, right near the surface. And it's worth being very explicit about this. And we happen to have somebody who probably is the world expert about this in the room, in Nathan, but these currents near the surface are extremely sheared. You need information about their vertical structure if you want to extrapolate between one instrument that might measure at 5 meters depth and another that measures, say, at a ½ meter depth. This is also physically significant because what's happening very close to the surface supports the fluxes between the atmosphere and the ocean. The atmosphere doesn't see the ocean at 5 meters depth. The atmosphere sees the surface of the ocean. So to extrapolate, we want to know if we can say anything about this vertical structure. So I'm going to focus on DOPVIS. This is an idea my advisor, Ken Melville, had been working on for a long time. We wrote a paper about this in 2023, and it's a relatively simple idea. We have a DSLR camera on an airplane. We fly that airplane at about 1,500 feet, and we very, very carefully georeference. And as we fly over some area, and when we fly at 1,500 feet, we can see about 4 kilometers, we're going to focus on some patch of the ocean surface. And we're going to carefully georeference and just look at that same patch as we fly over. And this is what it looks like. So this is a 256 meter by 256 meter square. And as we fly over, we're seeing waves propagating from the upper left to lower right. We're seeing all this transverse structure and some active braking. Let's watch this one more time. And you can see the resolution is changing, but that doesn't really matter. You're capturing a cube of data. You have information in space and you have information in time. And Stuart and Joy and Nathan told us what you do with those cubes of data. If you fit the return intensity to the linear dispersion relationship, essentially the difference of that intensity and the linear dispersion relationship can be used to estimate the currents at various depths. At a practical level for the flights we were doing, we have a horizontal current resolution of 128 meters to a kilometer, and we resolve a depth between a ½ meter and 3 meters. So we're close to the ocean surface, but not exactly at it. Now, I want to take a short break and just ask the question, which currents do these processes actually measure? Now, you're probably sitting there saying, what do you mean, which current? Like, what does that even mean? Let's take a half step back and remember our Waves 1 class, where we looked at surf deep water irrotational surface gravity waves. The free surface displacement is this white line here. I'm going to show you the Eulerian velocity field in blue and the particle trajectories in yellow. Just imagine we drop a little bit of dye into the fluid at a couple of depths. The Eulerian velocity is perfectly periodic, meaning if we take its average, it's going to be 0. The particle trajectories, you notice, are not closed circles. They're slightly open. This implies a transport in the direction of wave propagation, we define the difference of these averages as the Stokes drift. And we notice that this behavior is much larger near the surface than it is at depth. So there's this quantity we want to keep in mind. It's called the Stokes drift. And it tells us that when it's big, we have to worry about the difference between a Lagrangian mean, this one operator where we follow particles, or this Eulerian mean, where we're at some fixed point in space. Now, what does the Stokes drift look like for an ocean wave spectrum? These are LiDAR measurements from a day not unlike that shown in the video. The waves or the wind speed at 10 meters height was about 10 meters per second. The peak period is about 10 seconds. And we integrate over the azimuthal direction. And Kurt Kenyon, when he was at URI, taught us how to go from this omnidirectional spectrum phi to this Stokes drift. We notice this exponential weighting. So the Stokes drift decays very rapidly with depth, that evanescent decay, but it's quite large near the surface. It's 20 centimeters per second. Oftentimes the currents we care about in the ocean are not that different in magnitude than 20 centimeters per second. Yeah.
Just a quick clarification. What do you mean by surface? Is it all relative to
a mean water level? Yeah, C equals 0. So that's a great question. This is not in a curvilinear frame. When I say surface here, I mean the mean water line according to linear theory. So if you went down to, say, the shorter waves and you said something like this, depending on the reference frame you're in, that could be extremely problematic. The mean water level in the Lagrangian frame is an order of magnitude higher than in the Eulerian frame, so you do have to worry about that. Here, it's not going to matter so much. We're just making the point that this quantity, Stokes drift, which tells us when we need to worry about different kinds of means, is largest near the surface. At 5 meters depth, this has a value of about 10% of its value at the mean water level. So if you're in a ship taking measurements at 10 meters depth, you probably don't care about the Stokes drift or the difference of these means. If you're near the surface and you really want to resolve what's happening there, you might be very concerned about whether or not you're capturing an Eulerian or a Lagrangian mean. And so I'm not going to get into the details today, but we spent quite a bit of time. I wrote a JFM paper developing the equations of motion in the Lagrangian frame, motivated by some of the confusion brought up by Stuart and Joy about what HF radars are measuring. And we showed that DOP-Viz actually measures a Lagrangian mean current. I have slides at the end if we wanted to talk about this, but it's just a technical result. What I wanted to motivate is that you have to worry about what these instruments are kind of measuring and where. But let's look at what DOP-Viz gives us. So we're in an airplane that's called mowing the lawn. We fly across here, we're cutting off the lobes, we're doing a big turn, then we fly across here and we keep doing this. In color, what I'm showing you is the temperature. We had IR imagery on board, and we went from really warm water here to really cold water here. So this kind of looks like something like a thermal front. And just note this is 5 kilometers. And we see that in the velocity field of the currents. We have this strong southward flow here, and then this northward flow here. So these types of coincident and co-located measurements of various properties of the upper ocean are extremely uncommon. And so what's really nice, again, is we can see this information at the same time. And I'm showing you the currents at 2 different depths, minus 0.4 meters and minus 1.5 meters below the mean water level. Now, you can also look at how these things evolve over the course of a few days. So this is the rolling up of some mesoscale current feature here. This is DOP-Viz's velocity predictions on April 19th. And then you can go back the next day and see how this mesoscale eddy has evolved. So it allows you to kind of piece together what's happening to this system. SSTA is just sea surface temperature anomaly. And so you can go out for a flight. You're usually limited to 4 to 6 hours, depending on where you're flying from. But then you can go out the next day and take some more measurements. And you don't only need to look at the currents themselves, but you can start looking at gradients, as we've been talking about today. So it's very, very difficult to directly measure that vertical velocity, as we've been talking about. So what people have resorted to doing is looking at something called the horizontal divergence, which is just the horizontal divergence of the velocity field. And when delta is greater than 0, we think of the flow as upwelling. And when delta is less than 0, we think of the flow as downwelling. So the submesoscale fronts are all these things in blue, and you can correlate them between what you see the velocity field doing and what you see delta doing. This is an extremely difficult observation to make. There's only been a handful of these really ever where you get spatial maps that you can take gradients of at this submesoscale. And so just to summarize this warm-up part of this discussion, there's a lot that we learned from DOPVIS during S mode. Concurrent measurements of temperature, waves, currents, and current gradients were performed, but there are a lot of issues with what's going on here. There's finite flight speed, so it takes time to fly around and cover an area. So in those images I was showing you, for example, you might start their flight here. This might be 5 hours later. These submesoscale currents evolve on timescales where that might matter. So we're not getting an instantaneous snapshot. We're getting something limited by how quickly we can fly. There's limited depth information in what I'm showing you. And the other thing to note is there's asymmetry between the resolution along track. So in this direction, where we have a velocity field every kilometer, and what I'm showing you in the transverse direction. So you're sitting there, if you're still awake, and you're asking, why don't you just compare this to something in situ? Why are you using this remotely sensed estimate of the velocity field? Come on, we're ocean engineers, go out there, take a measurement. What's so hard about this? Well, the issue is shipboard measurements, if they have an ADCP on the bottom, they need to get out of the way of the superstructure of the ship. So ADCPs typically take measurements starting at about 8 meters depth, sometimes much, much deeper. Well, we live in the time of robots, so why not use an autonomous platform? Are there better ways to do this? And I want to talk a little bit about work I've done with liquid robotic wave gliders. Are there any, has anybody seen these before? Maybe they have some on campus. Okay, so these things are super cool because they go out to sea when you don't have to, when things are raging. This is a wave glider. This wave doesn't look very big. It's about 8 feet. It's about to smush this poor wave glider. And we send these things out for 4 to 6 week deployments, and then we pick them up. Here's us grabbing one at the end of the third field campaign for S mode. And these are the two lead engineers, Ben Hodges and Laurent Guerrier. And you can just see the excitement they have for finally picking these things up and having them be in one piece after being out at sea for 6 weeks. And so these things are actually pretty simple. They're kind of like surfboards, and they have this umbilical cord that's between 6 and 8 meters long that essentially connects to a pair of swim fins. This is one of those ideas where I think all of us think, why didn't we think of this? As the waves pull the thing up and down, it's basically kicking its way through the ocean. So you can do very long duration deployments because it's being largely powered by the waves. They added a propeller for the latest model. It doesn't work. You don't use it that often. These things are fairly quiet, so we've done acoustic work off the back of them. You can tow things. I'm going to talk about the payload shortly. But the main thing is they used to be cheaper than they are now, but they're very, very durable. You can send these things through hurricanes, and they still come out the other side. So what are on these? So we have a lot of meteorological information. We have met stations, 2 GPSs. We put sonic anemometers on them. There's two kind of generations, the SV2, which is about 2 meters, and the SV3, which is about 3 meters. The umbilical cord on the SV2 is 6 meters, and we wrap a T-chain around it. We put a downward looking, so what do we have? We have a Teledyne workhorse looking down, and then we have a Signature 1000 looking up on the sub, try to get those currents as close to the surface as we can. And then sometimes we drag a thermistor chain below this. And on the SV3, we can put a winch so that we can yo-yo something like a CTD sensor, like an RBR concerto. So you can heavily instrument these things. We sent 8 out during S mode, and they're all kind of similarly outfitted with Tom Farrar's group at Hui. And it really gives you a lot of information right at the ocean surface. This anemometer, sonic anemometer, is about 1 meter off the deck. So it's very, very close to the ocean surface. And you can get concurrent measurements that are extremely difficult to get in other ways. This is shortwave radiation, SWR here. So the sun comes out. This is off the coast of California. The day warms up. This is true wind speed, basically wind speed at 10 meters. The winds come up during the day as things heat up. And you can see that this is putting more energy into lower frequencies. So we start to see waves. And then all that heat that was near the surface from the sun beating down starts to get mixed to depth by those waves from Langmuir turbulence, essentially. This is an extremely rare type of observation. Jerry Smith did this in the 1990s. This is pretty much the second documented case where you see the mixed layer deepening and you can currently have environmental variables in that region. So these wave gliders allow you to see multiple different things at the same time above and below the ocean surface. We can also compare those wave glider measurements to what we're seeing from DOP-Viz. So that's what I'm showing you here. DOP-Viz are these triangles near the surface. This is just meridional and zonal velocity here. The upward looking ADCP are these squares, and then the circles are the downward looking ADCPs. And we see fairly good continuity between the two. And physically, we also see something interesting. The velocity behavior is not monotonic. There is a lot of structure in what's going on, particularly near the surface. So if you're assuming that these things are monotonic, say evanescent in the vertical, you might not be fully capturing what's going on. And if we average between 2 and 3 meters depth and compare what DOP-Viz is seeing versus the wave gliders, you see pretty good agreement between the two predictions. Now, I'm not going to get into it, but during S-mode, the thing I was pretty much trying to figure out for a while is what are wave gliders measuring in terms of their mean currents? So a wave glider goes up and down. It's kind of like a mobile buoy, but then it slides around on the face of the wave. So it's Lagrangian in the vertical, probably, but it's pretty much Eulerian or quasi-Eulerian in the horizontal. How that maps onto the mean is unclear. So the thought experiment is if there are no Eulerian currents and you had waves, what would these things measure as their mean velocity? That is not understood at this point. Yeah, of course.
How do you take the motion, or do you have to worry about taking the motion out of the ADCP from the?
Yeah, so we just average these over like 20-minute time series, but we have really good accelerometers on these. That's how we're getting the wave information. And so these are just averaged, I believe, but you can also do some correction for the waves themselves, the orbital motion. But you know, on average, the waves are going to contribute just their drift.
The motion of the package itself. It's moving.
Oh yeah. It's the two GPSs are crucial. So we did this at first with one, and it was a nightmare. And just having those two allows you to really take care of that. Great question. So these things are relatively slow. They move max a meter per second. So this is problematic for physical reasons, but I'll also tell you an anecdote. When I was a grad student, I was driving these, and when they're driven by iridium, and you have to crew them the whole time, and you're staring at marine traffic. And basically, when you're going through shipping lanes, you're looking at these tankers when they're like 2 hours away. They're going something like between 10 and 20 knots, depending on what's going on, and they don't turn, even if they can see you. And so there's some guesswork that goes into trying to get away from them. I was driving one once when it did get hit. We didn't know it until we brought it back in, and it had a huge dent on the side, but it still was able to perform the rest of the deployment. So these things are very robust, but slow. And that matters physically as well, because if you're trying to chase down currents that move at a meter per second with these instruments, it ends up being extremely difficult. So instead, what we did, and this spaghetti plot is a little bit nauseating, is we drove these things in patterns, ideally so we can compute gradients between them, and we let the flow sweep by us. And so instead of trying to chase these features during S mode, we did a lot of sitting after failing to chase them down during the first couple of deployments. And so just some conclusions from S mode. We performed some of the first of its kind measurements. There were limited direct measurements of vertical velocities. Again, we're inferring that vertical information essentially by computing these horizontal gradients. But horizontal divergence is also difficult to measure, as people in this room know. And so there's only really limited, those divergence plots I showed you are some of the first things coming out of that mission that were able to do that. I didn't show you anything really from doppler-scat, which was the main instrument that we deployed, because doppler-scat scatters off of waves about this long. And the way you go from the intensity of the return to the currents is through something called the GMF, a geophysical model function that's been very unconstrained. And so it's leading to a lot of noise that shows up a little bit in the velocity fields, but a lot when you start computing the gradients of those velocity fields. And so in general, there were a lot of questions during S-mode about what each instrument is actually measuring and kind of at what depth all of these instruments are measuring too. You know, Doppler scat, one other thing I'll say is it's scattering off of waves about this long, which should give you currents at about this depth. But Ernesto, the chief engineer behind it, was saying that his GMF predicted currents at 5 meters depth. And so if you don't have that vertical structure, you don't know how to go from 5 meters depth up to the surface. So what do? We can see what else has recently been deployed by NASA. And they have a satellite that launched in December of 2022 called SWOT. It's a surface water and ocean topography satellite. This thing is amazing. It's studying both the ocean. So it's an altimeter that goes around the Earth. It has a 21-day repeat transect, meaning it comes back to the same place every 21 days. And it's getting heights. It's getting the anomalies from the geoid. And it can give you sea surface height. It can give you river height. They're using this a lot to see during flooding events how much water there was. And already some of the papers coming out of it are absolutely amazing. So Jere did some work in southern Brazil on this, and there's a beautiful Nature paper in 2025. We've been using it to look at what are called iceberg tsunamis. So there are these massive chunks of ice coming off of Antarctica. This is A76A. It's an iceberg, which at the time was 110 miles long and 16 miles wide. So this thing's like the size of Long Island. It heads north. It hit the ground near South Georgia Island, and it chunked up into pieces that were many, many kilometers big. Now, what happens when you drop ice into water? No one gets hurt in this, just in case this is a little bit disturbing. But this is a much smaller amount of ice falling into the water. These are all people.
At least they're going in the right direction.
Should be the way it's final. So when you, basically this is like dropping a rock in a pond. You create ripples. These are much bigger than ripples. And you can see how efficient this momentum and energy gets radiated away when you perturb a free surface like this. Now, this is a 50-meter chunk. What happens when you have kilometer-scale chunks falling in the ocean? So the lead author on this is Tom Farrar. He's from the state of Indiana. This is the sea surface height anomaly. This is the outline of the state of Indiana for scale. So you are seeing ripples that are essentially self-similar to what you see if you throw a rock in a pond that are the size of a state. SWOT can see these. It's absolutely incredible what SWOT is able to pick up in terms of sea surface height anomaly. However, how you go from sea surface height anomaly to velocities is easy at a geostrophic scale. So mesoscale and larger, we can do that. Everything smaller, it's not clear how you can go from smaller scale sea surface height information to currents. These smaller scale sea surface heights are strongly sensitive to things like internal waves and internal tides. There's some hope we can like machine learn our way out of this first problem with enough data. The thing that is far more limiting for SWOT is that it has a 21-day repeat cycle. So if you want to know how a submesoscale current evolves on the time scale of a couple of hours, Too bad, you have to wait 21 days to get another snapshot of what's going on. So this motivates this recent paper that we have in press. It should be out in the next few weeks. We're just fighting with the people to finish up the proofs, and it's called An Unprecedented View of Ocean Surface Currents from Geostationary Satellites. So this is a project with Luke Linnane at Scripps, Kaushik Srinivasan at UCLA, and Roy Barkin at Tel Aviv. And what we're doing is looking at geostationary satellites and asking the question, can we actually measure from the submesoscale to the basin scale? Can we get currents across this whole range? And what we're going to do is look at these geostationary satellites. So this is GOES. It's an American geostationary satellite. We use these all the time to learn about weather. So in my weather class, this is what I'm often showing. 1 kilometer spatial resolution, 5-minute temporal resolution. It doesn't move. These things sit over the Earth and rotate with it. And so it's not like this 21-day repeat cycle. It's every 5 minutes we get a measurement. This is the key to what's going on here. Now you can also look in the infrared here, and then you have a slightly coarser resolution, 2 kilometers instead of 1. But again, 5-minute temporal resolution. We were doing experiments in the New England Seamount, and we were doing some path planning, and we noticed that you can see, if you look carefully through the clouds here, there's some structure underneath these. You can see stuff here and here. And what you're actually seeing are the currents. It might not be that obvious, but now let's download the data and just change the color axis. We're going to look at the same thing. This is the Gulf Stream. These are some huge eddies coming off the Gulf Stream. Some other eddies, some other things here, but lots of instabilities. So you can very clearly see between the clouds, and we'll talk about the clouds soon. That's what all this black stuff is here. You can see all of this thermal structure. And so Luke and I are coming from the water waves community, and we said, let's just do PIV or PTV. It should be super easy. We'll look at log rad T. It'll give us some more structure. So that's what this is, the log of the gradient of the temperature. And look at all this stuff. We'll be able to figure this out in no time. We'll just do correlation between frames. The time step is really small. It turns out that when you have these heavily braided structures like this, it's really hard to correlate again across frames. And so I went to grad school with Kaushik and Roy. I've been hearing Kaushik talk about machine learning for a very long time, since about 2012. And so we reached out to him, and he wrote a UNet architecture to learn how these fronts evolve from a turbulent field. So he took Dimitri's MIT GCM run of LLC 4320, 2 kilometer resolution, and an hourly in time. And we basically chunk up the North Atlantic. We don't want to learn the general circulation. That's not the point of what's going on here. We're trying to learn advection. So we kind of have a conditional statement. If you give me 3 frames of the log of the gradient of the temperature, can you give me the velocity field that would lead from one of those frames to the next? That is the question we're asking. We have this loss function, which is this convex function. It's an L1 norm here for the velocity. And then there's some spectral loss. We don't need to go through the details. And then we want to feed in the geostationary imagery. And out, we hope we get a velocity field. That's the game we're trying to play here. And so, this is some of the technical details. I don't want to dwell on it, other than we did a lot more sophisticated stuff than what I'm showing you. And it turned out a simple UNet without anything like generative diffusion was pretty good. And the key here is that unlike altimeters, we don't have to worry about the internal waves because they only weakly modulate the temperature field. And so there is a big advantage here for using the temperature instead of something like the sea surface height anomalies. So let's look at an example. This is just the SST off of the Gulf Stream. We're up here. And GOFLOW predicts the velocity field associated with that. So we see all this correlation between the velocity field and what the temperature looks like. But we also see this strong velocity in areas where the texture isn't so high. And so it is predicting some other stuff there. You can fix a point in space and see the inertial oscillations from the velocity. That's always helpful to make sure that's being reproduced. And you can look at this in this panel here. So this is what I just showed you. This is the log of the gradient of the temperature. And then you can start looking at gradients like the vertical vorticity here. So until these measurements, no one had ever been able to do this except in models, and especially the divergence that you're seeing here, where you have all this upwelling and downwelling from these features coming off the Gulf Stream. These are kind of holy grail measurements that people have been trying to get, and until this point, we had only seen them in models across these scales. We can look at the time evolution where you do see some inertial oscillation. It's a little bit hard to see what's going on, but you can look at, for example, some of these eddies to look at the evolution of the vorticity. And in the paper, of course, we had to spend quite a bit of time trying to get some sense of whether or not we could validate these in situ. So we were performing experiments on the New England seamounts for an O&R project, and the RV Armstrong was going across this eddy. That's this velocity field here. And we can compare that with what GOFLOW is predicting, and that's just a bunch of times from GOFLOW. And in black is what the Armstrong is measuring with an ADCP. We also compared this to a bunch of drifters, SWOT velocities, etc. We're not going to dwell on that here. I think the takeaway is that until this product was available, if you wanted to know what the vorticity looked like out in the Gulf Stream, you'd have to go to an altimeter like a Pizzo, and you can compute the vorticity from a Pizzo, and it looks like this. This is what GOFLOW gives you. So again, this is what we used to have. This is GOFLOW's prediction. So it's like, yes.
So that big warm core eddy, in the currents, it looked divergent. Like, is it really that strongly divergent, or is it just how you have the arrows drawn?
This is the vorticity. So we can look at the, oops, wrong way. Let's look at the horizontal convergence and divergence. So it is the eddy. This is the video.
It's under the cloud.
Let's go back to here. So the eddy's here. So you can see all of this frontal behavior here and here.
But the large scale is just an artifact of your arrows.
I believe so, yes. Yeah, I think that's almost even the arrow head size, actually. And so they're quite dense there, but there is some frontal features along the edge.
Be interesting to compare it to the oleander data.
Yes, okay, that's a great idea. I totally agree. So again, we can start to get higher resolution of these current predictions than what we had in the past. This is GOFLOW here for the vorticity, just zooming in on the Gulf Stream. This is what SWOT gives you. Again, SWOT will likely be able to do better than this in the future. There's a lot of noise here, but it's severely limited by the fact that it'll be back 21 days after this. And then this is what a Pizzo gives you. Now, what people like to do in GFD is characterize these flows based on joint PDFs of particular velocity gradients, like strain normalized by the Coriolis parameter and vorticity. And then the contours here are just, this is a PDF. In green is what a Pizzo would give you, so that relatively low resolution product. In white is a 30-kilometer filtered version of GOFLOW. And then what you see here is all of GOFLOW. So you see this strong asymmetry. This is because there's an instability, symmetric instability that takes over if the vorticity is less than -1 here. And you see that this large part of the distribution with high vorticity and strain is driven by these regions that have strong horizontal convergence. So these are these fronts in the ocean. And those are correlated with these large gradients in temperatures. So that's what's supporting kind of the extreme parts of these distributions. Okay, so just to summarize, and I want to end so we can, so how much, this goes till when? 4? Okay, so I'm going to end in now, basically. So this is a lot of information. The main thing is these satellites already exist. They're all over the place. You can do this very well, except at very high latitudes. So now we're going into the Med. You can do this in places like the South China Sea. There are lots of geostationary satellites available. So we've been developing more of an operational product for the Navy for this. And I'm going to skip all these videos. Thank you for listening.
We have time for a few questions, and afterwards we'll have more time at tide night. We'll be heading over there. But if you have questions now, please ask them.
Really? Do you get, are you able to look at concentration of sediment from the visible part of GOES?
So that's a really good question. We've been talking to Agatha Pfeiffer Braga, who did her PhD at UMass, and there was a very large discharge out of the Rio Grande do Sul in southern Brazil during one of those flooding events. And you can see in the visible the sediment. You can see, yeah, it's clear. Because the resolution is so high with GOES that we were surprised, but you can see things near the coast.
Because I wonder, different wavelengths will attenuate at different depths. You have infrared, which is interfacial.
Yep.
And that, have you thought about extending this to get a velocity profile?
That the dream here, the thing I want to do is do decorrelation length and time scales between the ocean and the atmosphere. Like for example, the Gulf Stream is thought to be a storm attractor. But you can also do this at depth and start seeing how much you can actually get from surface information to information at depth, corroborated by the thing that you're talking about.
So two things. Have you heard of the Glimmer mission that might or might not ever leave from UNH? It's basically geostationary high resolution hyperspectral.
Oh, cool.
Strikes me it would be useful. Joe Salisbury's the PI on that. They built the instrument. Now it needs to go into space. Going back to the Lagrangian picture,
Sure.
you showed at the very beginning, I do a lot of work looking at how larvae and passive tracers are moved. How would you interpret that if those particles were also responding to the turbulent field? So they were being mixed up and down.
Yeah.
Is there some sort of net Lagrangian? Does it get?
So work we're doing right now, I worked with a guy named Greg Wagner, who's a modeler. He wrote Oceanography, which is a often used now upper ocean model. The equations of motion that we solve in this system, like the Craig-Leibovich equations, for example, are actually Lagrangian mean equations. And so they do move the material physically. And so there's an interaction that occurs between the waves and the turbulence. So my OSM talk, and I guess you can't see the title, so let me move this, was about how surface gravity waves actually organize turbulent flows in these types of upper ocean environments. And you can see these waves actually catalyze these jets in the upper ocean that people have been seeing for the last couple of decades. And that can lead to additional transport. I can send you the details or whatever.
That would be one. I'll
Yeah,
come up.
but that's kind of a holy grail question in water waves, is how do waves impact the turbulence and vice versa.
So I just want to check my understanding first. So you estimate velocity from data concentration, right, using machine learning?
Kind of. We're making a conditional statement that if you give me a temperature field at some time t+1,
Yeah.
another one at t, I'm telling you a velocity field that would affect that distribution at t to that distribution at t+1.
So have you ever tried some more traditional approaches rather than machine learning? I know that there are similar techniques to do that, something like optical flow.
Yeah, so we tried
How
that.
about,
That's basically what we're trying to do with the PIV,
Yep.
Particle image velocimetry. It's like if you, in fluid flow in the lab, if you want to track a velocity, you can put a bunch of glass beads in, shine a laser, and they radiate, and then you can track them, correlate them between frames. It's kind of like optical flow.
Yep.
It doesn't work when you get this heavily braided structure. It's very hard to correlate it across frames, we found here. People had tried to do that, I think, like 5 years ago using geostationary satellites, and also found it to be extremely difficult. So we did not want to start with any of the ML stuff. I would say we're kind of more classical, or historically were, and so we were kind of cornered into this. I have a student now who's trying to figure out what these models are actually learning from the physics. So he's taken the Johns Hopkins DNS data 3D turbulent data set and throwing GOFLOW at it to try to back out what GOFLOW is actually learning. Because we don't know.
Does GoFlow do the declouding too, or do you?
So the declouding, our name for this project was Between the Clouds. That's what we called it amongst ourselves. And so we had 3 days of no clouds, and that resulted in this paper. The clouds move at a different speed than the currents. So that's one scale separation. That's not enough to get rid of them. We're going over the med next because the med will have long periods of no clouds. But we want to combine this with like microwave information that sees through the clouds and eventually figure out a more esoteric or better way to get rid of the clouds. But that is the major issue. And if you do this at polar latitudes, what are you going to do? You know, but we're writing a paper right now doing some structure function work because of the clouds. You can't do things like coarse graining. Like any spectral stuff with clouds is not good. So we're doing some third order structure function stuff to look at energy fluxes.
Okay, if there are no more questions, thank our speaker also joining us.